Before we tackle the second order equations, or higher order equations, I want to look at this very simple first order linear equation. Y prime plus AY equals to 0. And it's easy to figure out using techniques we've already studied that the solution to this problem is y equals to a constant, c, times e to the negative ax. So let's verify that. If I take this derivative, y prime is minus ac e to the negative ax. And if we plug it in up here, we have minus ac e to the negative ax plus a times y plus a times ce to the minus ax. And look at that, they cancel. Equals to 0. So it works. And it gives me an idea that if I have constant coefficients of my y's and my derivatives of y, that perhaps the solution is e to a power related to those constants. So I'm going to use that idea and solve a second order equation. Here's a generalized second order linear differential equation with constant coefficients. So a y double prime plus b y prime plus cy equals to 0. And actually it's because this equals to 0, it's also known as a homogeneous equation, homogeneous differential equation. So we run into that term homogeneous in various areas of mathematics. Another place you see it is in linear algebra, a system of equations in which the right-hand side is all nothing but zeros. It's called a homogeneous system of equations. So here we have let's classify this as a second order linear. It's linear because we're not multiplying y's and y primes and stuff together. We're not multiplying y's and its derivatives together. Second order linear differential equation, a homogeneous differential equation with constant coefficients. All right, it's the simplest kind of higher order, general higher order equation you can imagine, I would believe. And my idea is this: I'm going to do a trial solution here. I'm going to let y be equal to, I'm going to call it c1 e to the m times x. All right. Now I didn't want to confuse this constant with letter c here, that constant. So I'll call that c1 for now. And letter m, turns out, as we find out, it ends up being kind of a traditional letter in differential equations. So that's why I used m. All right. So I'm going to make an assumption that that may be a solution to my problem. And let's just check it out and see if it is. So the first derivative would be mc1 e to the mx, and the second derivative would be m squared c1 e to the mx. So if I plug these into here, I've got ay prime will be, let me see, it's going to be a c1 m squared e to the mx plus, and by prime will be b c1 m e to the mx, and then c times y will be plus c1 times c. So I think I'll put c1 e to the mx, and equals to 0. Great. So let's see what we have here. And one thing that I can cancel out of this equation. I can divide by c1, this constant, and I can divide by e to the mx. Now, you got to be careful dividing by anything with a variable in it, because if you divide by a variable term and it happens to be equal to 0 at some point, you're going to lose an answer somehow. So, got to be careful with that. But in this case, we're all right because e to the mx is always positive. It can never be 0. So I don't have to worry about division by 0, any of those issues. And c1 and both e to the mx appear in everything. So if I divide the whole equation by this, then it simplifies quite a bit here. what I end up with is am squared plus bm plus c equals to 0. And if I now solve for m, which we could do by using the quadratic formula if we like, then we will be able to write an answer. Now, the neat thing about this is when I solve this, most of the time I'm going to get two answers. And I have two answers because it's a quadratic. And so really our answer is going to be a sum of two terms here with different values. Now let's suppose that we went ahead and solved. And this led to finding two roots, m equal to root 1 and root 2. So I'll call it R1 and R2 for the two roots of this equation. In that case, then each of these will give us this kind of answer. That means my solution then is y equals to a c1 times e to the r1x plus c2 e to the r2x. So because each of these in and of itself, each of these two terms will work up here. And it's kind of easy to verify that by literally going through there and realizing that when you plug R1 or R2 into this equation, it does equal to 0. So that's basically the solution to this problem and in abstract form. So I'm going to erase all this and work a few problems with real numbers in it.